Good afternoon or good morning, and thank you for attending today's webinar, Introduction to Surface Finish Filtering, Selecting the Correct Wavelength Cutoff. Today we're going to learn about using filtering and surface finish measurements, what makes up the surface profile, what can go wrong with measurement results, talk a little bit about understanding filtering and filtering of different types of surfaces. So why is it important to monitor surface finish? Well, as dimensional tolerances tightened over the years, form and surface errors have become more significant, and tighter tolerances are required for products in aerospace industry, electronics, automotive, medical, and precision manufacturing. And every surface has some function, and unless it is measured, one will not know if the product performs as desired. And so why control surface finish at all? Well, there's a few important reasons. A pretty obvious one is appearance. Surface finish affects reflectivity and consistency. And as you can see in the picture on the right here, surface finish can make the surface shiny, or it can make it dull and not so reflective. So monitoring surface will make consistency between parts better. There's also surface function. Adherence of coating is an important feature. If the surface is too smooth, maybe the paint will not stick, or if it's too rough, the surface finish might actually show through the paint covering. So again, to monitor the surface for coatings is very important. There's also surface interaction. You know, on sliding surfaces, you might want to reduce the surface finish to have less friction, but you may also want to create a specific roughness that allows for gaps to exist within the surface to let oil fill them and increase the lubricity of the surface and let the oil do its work. And also you want to check the surface to maximize the process, because you don't want to have too much machining time on a surface that's really not required. So by having a good surface control, you can achieve what the spec calls for in the most productive way of time. And also you can use surface finish to analyze process problems. If the machine is breaking down, for example, you might see that coming through as a surface finish problem. So where does the surface finish come from? Well, it comes from the manufacturing processes. So most machining process produces three elements of the total profile, with roughness usually being the most influential. So here's our typical lathe, for example, and it has a motor and a gearbox, a pulley going through some bearings to a rotating spindle, and on the carriage is the tool, which is part of the lathe, and all those different parts of that machining process puts its own signature on the surface of the part. So you can see things from roughness from the tool marks, vibration or waviness from the motor, or bearing issues, straightness or errors of form from the bed lathe, for example. And they all get tied together into one surface. And so it's important to be able to realize that, but also to pick out the parts of that surface. And that's what filtering does for us. So how do people measure surface measurement? Well, it started with the scratch standards, and people used to use their thumb against a reference to estimate what that surface is. But now there are some very sophisticated methods for the measurement of surfaces. Most of them are mechanical contact types, but today optical 2 and 3D imaging is becoming a very important way of monitoring surfaces. Again, as tolerances get tighter, surfaces have more custom features required. Optical might be the way to go in some applications. But still, the contact method is still the most common. We provide two types of contact measuring system. Mostly the roughness instruments, which are a skidded measuring system, which has a skid, which is moved over the part, and within that skid is the probe that, or the pickup, which is monitoring the actual surface finish by a very small diamond contact usually. So the skid filters out a lot of that waviness, and it only produces only roughness parameters. The waviness is filtered out by the skid that's following the surfaces, and most portable instruments are the skidded type. Mahr also produces a skidless measuring system. These have a built-in reference built into them and a precision probe or pickup that's again moved over the part. So now because of the internal reference system, the probe can pick up not only the roughness, but also the waviness parameters. So two different systems operating similarly, but producing two different sets of data. And there's lots of ways to analyze the surfaces. There's over 100 different parameters for surface finish evaluation. And they can be targeted or customized to check the stability of the manufacturing process, the functional characteristics of the surfaces, that the analytical capabilities can do some very complex analysis of the surface. But in today's world, RA is the most common, but in the rest of the world, there's also RZ and RMAX. So between those three parameters, 95% of the parameters are probably covered. And they're all dependent on the length of the measuring process. I mentioned it briefly, but what is surface finish filtering? Well, surface finish filtering is the method by which a surface profile is separated into the different components. Now, we talked about the surface having the different parts of the process, the waviness, the roughness, the straightness. All those things are a part of that surface manufacturing process. Filtering allows us to separate those things. We can pull out the form errors. We can pull out the waviness profile, leaving only the roughness parts of that profile. So filtering is a way to separate the different components for analysis. So we need to make sure that when we do sample the surface, we do it in a manner that allows us to capture the wavelengths that we are interested in. So you can see here's a surface. You can see there's a waviness component to it, and we want to be able to pick out the certain part of that that gives us the best information of just the roughness, for example. So profiles, have those different components imposed upon it, and again, filters are used to separate the wavelengths so that they can be analyzed. So that filtering of the data, we want to exclude the unwanted data and keep what's important to our analysis. Now, there's different types of filters. When we talk about the probe going over the part, well, that's a mechanical type filters, and there's different radius of the probes. There's a 2 micron and a 5 micron, different types of radius, and they'll filter the profile or the roughness a little bit differently. And there's really nothing you can adjust with that. You get what you get based on that probe. But there are digital filters that allow us to separate the different parts of the profile. There's RC filters which simulate the old resistor capacitor type of filter out there. There's Gaussian filters, there's robust Gaussian filters, and these are all mathematical formulas which the signal passes through, which can filter out the data that we don't want to see. So it's very easy for the user to do. All that math is done within the system. So the user selects the cutoff setting used by the filter to separate the profile into roughness and waviness components. So filter data is always centered around a mean line. So the cutoff value is the longest nominal wavelength to be included in the roughness value. Wavelengths longer than the roughness cutoff are included in waviness parameters. And these cutoffs, we talk about cutoffs and cutting off parts of the wavelength and so forth. And I like to think of it as basically just like a sieve when we want to filter out something. And that's basically what surface finish filtering is. On a sieve, you'll have a mesh, and there's different size meshes out there to grade or filter out the different types of particles that might be going through the sieve. And that's what's happening with our filtering. A whole bunch of gravel, for example, might be put onto the sieve, and it's all separated into the different sizes that won't pass through there. So we can now separate the sand, which is like the roughness, from the gravel with the waviness, which we don't pass through that filter. So that's what's filtering is doing. It's allowing us to take away parts of the total surface profile. So typically a profile is broken into 7 sampling lengths, and the first and last are taken off to give us the data. You know, the first and last usually are removed allow for the system to pick up speed and to end the trace in the proper format. So basically what we're going to do is cut off the ends, the first and last one, to leave us with 5 measurement pieces of data, and the result of that becomes our roughness trace. So the waviness is removed from the profile. And that's what the filtering does for us. It allows us to choose the cutoff that's going to separate the roughness from the waviness components. You can see in this, the top picture is the total profile of the part, and we can select different cutoff lengths. We don't want to take that whole first one, the one that's labeled C1 there, because that has some profile component to it. We want to take the shorter segment, but when we properly select that cutoff, the waviness component is removed and only the surface roughness profile results. And that's what we want to look at. Now, through the standards, there's been different cutoffs selected and established to exclude the longer wavelength or the waviness. And these are defined in various ASME standards and ISO standards. And typically the cutoff was defaulted to 0.8 millimeters. But in today's world, we want to have people put that cutoff length as part of the surface roughness parameter, so that if a person is going to measure the surface roughness, they know precisely what to set the roughness filter at, so everybody gets the same reading. So there's a whole table of different cutoff or filtering lengths which are established in the standards. But you can see here's some example of the effect of roughness cutoff on settings. So here's an example of roughness with the cutoff set at 0.08 millimeters, and we get a roughness average of 0.560 microns. Now, if you change that to 0.8 millimeters, the RA goes to 1.149 microns. So by changing the amount of data coming through, you can see you have a very big effect on, for example, the roughness parameter. And unless that cutoff is specified as part of the parameter, who knows what the right answer might be. Here's some more examples of having different cutoff lengths can really give you very different roughness averages or RZ values, maximum peak to peak count and so forth of these profiles. So which is the correct one? The choice of cutoff is important to correctly evaluate the roughness profile, because you want everybody measuring your part or everybody measuring those types of parts around the world to get the right results. So it's important to pick the right cutoff to make sure that you get the right results. But fortunately, all those rules for selecting the cutoff has been put into standards or international standards. ASME B46 or ISO 4288 are all standards that designate the proper methods for establishing the right filtering for different surface finishes. So like I said, the cutoff should be specified on the drawings, but if the cutoff is not specified, there are guidelines in these standards for selecting the correct cutoff. Now, Mahr, like lots of other companies out there, provides posters that or data that provides information about surface measurement, the different parameters, and so forth. And all of this information comes from those standards. We also put as part of this poster the specifics segment, which is highlighted here, that talks about how to select the right cutoff. So if you want one of these posters, don't be afraid to email us or email me, and we'll be able to get this poster to you. But this selection of the cutoff is really the basis of what filtering is all about, to ensure that the right cutoff is selected and we get the right results. So the standards go through a whole dissertation about selecting the right cutoffs and how to do it. And the first question that you have to ask yourself, is the profile a periodic or a non-periodic profile? And what does that mean? Well, a periodic profile is very regular. You can see the top one, you can see maybe distinct tool marks. It's a very repetitive pattern. A non-periodic profile is more random. You don't see that. You can just kind of look at it and say it's repeatable or it's not repeatable. So here's again that periodic profile. It's a repeating profile, turned surfaces. There's a distinct direction of the cutting tool, for example, and you can cut over you can trace over the high spots 90 degrees to the profile, and you can get a good roughness measurement. A non-periodic profile there has no repeating profile to it. And these are very typical of ground or polished lapped surfaces, for example. There's no really pattern to these non-periodic profiles. And you can look at the different surfaces under different techniques, and you can't see that very distinctive periodic profile. There's a surface roughness there, but it's very well, it's not repeating. Again, there's standards that allow us to determine that cutoff, and refer to these standards for a periodic profile. The keys that we like to use is the RMS profile, and that's again part of the tables that come on these various charts on those, and roughness SM is the mean width of that profile length. So you can look at that repeating profile. You can see that there's a repeating process here, and what we're trying to look at is the length of that process. And if we look at this selection guide, that's part of the table or part of the chart that are available. You can look at what the RSM value is based on the measurement, and then select the right cutoff based on that parameter. So you can see again this profile. We looked at RMS, We measured it. It came out to 0.4 millimeters. We can go to our chart, where our chart says what's the RMS value, RSM value. It's up to 4, so that we should select 0.8 as our cutoff value. So we can measure this, and as long as these two values agree, then we can say we have the right cutoff for that type of profile that we're seeing. And this chart is very valuable for helping people select the right cutoff for maybe an unknown surface profile that they're measuring for the first time. But for non-periodic profiles, it's a little more complicated. There's a number of different parameters that should be used to determine what the cutoff length might be. You can use RA, RZ, and RSM as part of the analysis to try and get the right profile. And again, the table provides the capability to select which one of the profiles are going to lead us to the right results. So again, here's our table for selection of cutoff. Now the first one was a periodic profile. Now here's our selection for non-periodic profiles. So we can look at RZ, we can look at RA, get our measurement results, and the cutoff table will give us the correct results. So again, RA is our mean roughness, and RZ is the roughness depth of a single vertical distance over the measurement length. So we took a specific example. Here's a case where we have a non-periodic profile. The R sub A is 1.5 microns, so we can find our value there. We can get our results, and it comes out to 0.8. So we can get our cutoff length again based on the RA value. But for non-periodic, there is some other guidelines because it's non-repeatable. We want to make sure that we get the right value. And again, the standards are there to help us do that. And they also want us to, part of this process for non-periodic profiles is to make sure that we have the shortest cutoff length should be checked. So if we got a 0.8, for example, cutoff recommendation, we should check to make sure that if we went to a smallest value, we don't get a agreement within the table to give us the right answer. So what we're going to do is we're going to, according to the standard, it's going to be generally necessary to perform a second measurement with the next smaller LC value, or next smallest cutoff value. And only if it's proven that the next smaller value does not meet the requirements, then you can be sure that the value selected the first time, in our case, the 0.8, was the correct one. So periodic, here's our chart. Periodic is pretty simple. One trace using RSM and the chart. If everything agrees, we got the right cutoff length. With non-periodic ones, we're going to do our trace, going to get a value based on RA, and we're going to go one step smaller, check it again to see if our data agrees with that or not. So use RA. If everything agrees with this next smallest one, then we're good. So here's an example. We've got an RZ of 93 with the 0.08 cutoff. Here's an RZ of 0.84 with the 0.25 cutoff. So which one's correct? Well, it's based on the two readings that we've measured. We're going to make sure that the 0.8 comes out as our value for RZ, which is 0.93, which is between 0.5 and 10. Okay, now we've gone to a smaller one of 0.25, And this one, you can see that the R sub Z is over this value. So this is not a good reading. The 0.8 was the proper one to use in this case. The same thing can happen and we can do another example of by selecting different cutoff lengths, making two traces, we can verify that by using the 0.8, we get limits that fall within the tables on our table selection guide. So it's not so rare case that two different RFC values conform to the proper standard specifications, but the ISO determines that we should use the smaller of the two values when they come out to be quite the same to ensure we get the proper value. So the smaller one in this case is the proper one to use. So again, which one is correct? If there's no cutoff on the print, we use the standard 0.8 millimeter cutoff as the starting guideline for most measurements. We've used a 0.5 millimeter waveform was filtered out, and we've got the proper periodic profile, an RA providing a result of 6 microns. You know, there's lots of different parameters with surface finish. You know, we got our filtering, we got the length of trace. But what we tried to do today is that we tried to cover a little bit about what the surface profile is. By using different like cutoffs, we can filter out the information of the waviness parts of the profile and just leave us with the roughness parameters. We've seen how changing the tracing length can affect the results. We talked a little bit about part-to-part measurements and how that can get different cutoffs with the whole idea being able to have a standard which everybody uses. The long wavelength components are important, but if we're measuring roughness information, we want to filter those out. Longer cutoffs are usually specified as conservative control, but there are some times we might want to use a smaller cutoff value. But we always want to use what's called out on the print. And that's the whole idea, is that engineers should be able to design the surface measuring the right profile or right roughness parameter that's measured, what that value is, and the cutoff length should be part of that, that indication or that tolerance on the blueprint. So why Mahr? Mahr has a big, broad product range for industrial metrology. We've got the competence to support you. We've got lots of innovative products, especially in the surface, the portable surface world. And at the end of this recording, we're going to send you this webinar. If you want a poster of the surface finish parameters, you can respond to that, asking for that, and we'll send that to you also. So again, thank you for attending today's webinar. Hope we talked about some of the information about filtering and gave you a little bit clearer picture of how filtering works to help you measure your roughness parameters. Thank you again.